Thanks for having me here. Today we'll talk about some of our recent efforts towards answering the question, what is my data worth? So we all know that data is new oil. It has driven great progress in current economy, and it has powered many applications such as targeted advertisements, speech recognition, and smart healthcare through machine learning. And all these applications have led to great, tremendous profit. And in many cases, the data come from people, but the problem is that those people who contribute data are not getting sufficient benefits from their data. Some economists, activists, and politicians start to argue that people should be get paid for their data, but the million-dollar question is by how much? Data is very hard to be priced. It is very different from the commodities that we have seen every day. It is different from this physical objects, and it has this non-rivalry property, meaning that if one person is holding a apple, the other person cannot be holding the same apple at the same time. Well, whereas for data, the same piece of data can be copied, transferred, and utilized by multiple entities at the same time. And the value of data will aggregate if you use it for multiple times. Because data is very different from what we have seen in nowadays in daily lives, so we cannot really copy the concepts and methods to in analog world to value data in digital world. There are some prior work in data evaluation. Some most popular one, like you can evaluate aggregate data set using the amount of queries that you performed on the data. Some recent work has also tried to differentiate the price between different queries in order to get some good properties. And people have also considered how to design auctions to price data, and even train a machine learning model to predict the price of data based on some attributes of the data set. But the limitation of all this work is that it cannot really address a common scenario where the data in a data set comes from different individuals. And the question there is that how can we price each individual's data in an equitable and reasonable way? So to talk about our data evaluation technique, I want to first talk about some general properties that we want for a good data evaluation technique. So we have been collaborating with a real-world data marketplace where people can upload their videos and images. And this data marketplace want to enable their customer to buy machine learning models trained on the data available on this platform. For instance, there is one person saying that I want to train a cat versus dog classifier using the data on this platform, and I'm willing to pay $100. And at the end, he or she will get a machine learning model trained over 1.5 billion images on this platform. And the question we want to answer is that how should we distribute this $100 back to different data contributors? So one naive way is to just uniformly distribute this $100 to all the data contributors, but it doesn't work always. So if you take a close look at this animal here, it isn't a cat. So many data points on this platform are actually mislabeled. Clearly, those mislabeled data should have lower value. So how can we actually ensure an equitable way to value data? And second challenge is that there are so many images. Practical machine learning models involve millions of data contributors. So we really need to have a way to value data that can scale to this million images or million data contributors. And in addition, we need to really respect some unique properties of data as commodity. As I mentioned earlier, data often comes from different sources, and the value of one data source really depends on the existence of other data sources. For instance, if we have similar data without your data, my data might be valuable, but if you also, we join the same machine learning task, then our data's value might diminish. So there is some combinatorial analysis that we need to perform in order to figure out the value of data given the existence of other data sources. And secondly, the value of data is changing. This is the performance of a machine learning model on the same standard benchmark data set in computer vision. And you can see that we get better machine learning performance every year. And that means our data is getting more and more valuable as time progresses. So here, the takeaway is that the value of data is really outcome dependent. It depends on how the data is used and what is the performance of machine learning model trained on this data. And thirdly, data can be used for multiple times. The same piece of data can be used to serve multiple tasks. And the more you use the data, the more more value you can get out of the data. So we need to think about this cumulative value when we think about the data value. Okay, so our framework is the first one that try to formalize these different properties and try to have a unified way to address all these different properties in a single framework. And to accommodate the first property, combinatorial property, we model machine learning as a cooperative game in order to model the combinatorial interplay between different data sources. So cooperative game has two components. One is players, the other is utility function. In the machine learning context, the players will be different data contributors or our training data. And in machine learning, these data points will be fed into a learning algorithm to produce a model. And then the model will be evaluated against some validation set, and we can get some performance measure for the model. And the utility function in the machine learning context will be a function that can map any subset of data points to the performance of the model trained on that subset of data. And to accommodate for this outcome dependence property, we reduce the data valuation problem to a profit allocation problem. So we look at what is profit of the machine learning trained on all the data sources, and then we try to allocate the profit to different data sources. So you can think about if your model is working better, then you kind of have a larger pie, and each data contributor can get a larger slice. And then we look at the other two properties, cumulativeness and equitability, and ask ourselves, what is the profit allocation scheme that satisfies these two properties? It turns out that in cooperative game theory, there is a unique solution that can allocate profits with these two properties. And that solution is called the Shapley value. It was originally proposed by Lloyd Shapley, a Nobel Prize winning economist in 1950s. So what is Shapley value? I'm gonna define it in the machine learning context. Imagine you have n data points, and the Shapley value will assign a real value score to each data point in the training set, so that the scores will be add up to the total utility of the data set. And the Shapley value is defined here. So n is number of data points, d is our data set, and s is a subset in our training data set. And the U is utility function in the machine learning. You can think of it as some performance measure like accuracy and so on and so forth. And if you take a look at the terms in the brackets, it measures the marginal contribution of the data points that we want to value to some subset S. And the intuition about the Shapley value is that the Shapley value of a data point measures its average marginal contribution to all possible subsets in the training data. And I mentioned that there are some good properties of Shapley value like equitability and cumulativeness. Let's see how it is defined mathematically. So equitability says that if two data points, adding them to any part of other data result in the same performance change, then they will have the same Shapley value. And if you add a data point that doesn't change the performance at all, then the data point will have zero Shapley value. And the cumulativeness basically says that if you use the data for multiple times and each use is associated with some performance measure, then the value under the sum of performance measures is the sum of value under each performance measure, which is quite natural. So although Shapley value has its good properties, there are significant challenges to use it in the context of data valuation, because if you take a look at its definition, this summation here involves exponential number of terms. And even worse, in the machine learning context, evaluating this utility for once is already very expensive because that needs us to retrain our model on this subset of data. So existing work try to handle the computational challenge by treating the Shapley value as a expectation of marginal utility of a data point to some random subset. And we design the probability distribution for the random subset so that we can match the constant in the definition. And then we can just use the sample average to approximate this expectation. More specifically, we draw some random subsets from the distribution and then take an average of the marginal contribution to each random subset that we draw. So this is the underlying mechanism to calculate the Shapley value in almost all of the existing work. And the prior work shows that if you want to achieve a bounded approximation error, we need to evaluate the utility function for n log n times. And that's actually a big improvement over calculating the Shapley value exactly, which requires exponential complexity. But still, in the context of machine learning, we cannot afford to retrain our models for this number of times. So the technical contribution of our work is really to develop some scalable way to calculate the Shapley value in the context of machine learning. The first idea come into our mind is that can we really improve this Monte Carlo method? Can we use fewer utility evaluations while achieving the same bounded error? And we wrote a paper to show that to show a positive answer to this question, and we show that we can actually reduce the number of utility evaluations by a large amount. While achieving the same approximation error, especially when the number of data points or players is large, our improvement is tremendous. And the key insight is that we leverage some information sharing between different random samples to enable a more efficient algorithm. This algorithm is really useful because it can be applied to some general profit or cost sharing problems. But if it's think back about data valuation, we still need to retrain models for multiple times, and it is not gonna be scalable to some large models and large data sets. So then we write a second paper and try some different ideas to improve the Shapley value calculation. Specifically, we try to leverage some characteristics of utility functions specific to machine learning models. So we focus on the k-nearest neighbor, which is a very commonly used machine learning model and develop a efficient way, a scalable way to calculate the Shapley value exactly. And I'm gonna show some results to compare the performance of our algorithm with some existing work. So there are two almost concurrent works for data valuation in 2019, and the maximum size of data sets that they value in their paper is 60,000 data points. While in our paper, we show that we can value 10 million data points in 44 seconds on a single machine. And we also compare our methods with the existing baseline in terms of scalability. And we show that our methods is exponentially better than the existing baseline. For future work, we would like to explore some how we can value data efficiently for some general machine learning pipelines. And another interesting question is that Shapley value is a ex post data pricing mechanism in the sense that you have to use the data in order to value data in a fair way. But in many cases, we would want a data price before using the data. We want to kind of carefully think about the trade-off between the benefits that we can get out of the data with potential privacy loss. So we will need some kind of anti-data pricing mechanism. And we also want to explore some potential applications of our data valuation mechanism. And that concludes my talk. And I would like to thank my collaborators and thank CLTC for the great support. And I'm happy to answer any questions that you might have.